Good morning, ladies. Unfortunately, I'm not feeling overly well today and I'm not going to be in, but I have a short little presentation for you to get you started on working through X-linked traits. So, I'm going to finish off first with the video that we were looking at last lesson by the Khan Academy. It's about 5 minutes or so of that to remain, and then I'll have a short PowerPoint presentation, and then for most of the rest of the lesson you'll do the work that the replacement teacher is going to pop up on the board for you. I've either sent it to you by email or it's on the front page of our class wiki. Alright, Khan Academy start.
But everything I've dealt with so far is, this is clearly plays a role in determining sex, but you do have other traits on these genes. For example, and the famous cases all deal with specific disorders. So for example, color blindness, the genes or the mutations I should say. So the mutations that cause color blindness, red-green color blindness, which I did in green, which is maybe a little bit maybe inappropriate, color blindness, and also hemophilia. This is an inability of your blood to clot. Actually, there's several types of hemophilia, but hemophilia is an inability for your blood to clot properly. And both of these are mutations on the X chromosome. Mutations on the X chromosome. And they're recessive mutations. They're recessive. So what does that mean? It means both of your X chromosomes have to have, let's take the case for hemophilia, both of your X chromosomes have to have the hemophilia mutation in order for you to show the phenotype of having hemophilia. So for example, if there's a woman, and let's say this is her genotype, she has one regular X chromosome, and then she has one X chromosome that has the, I'll put a little superscript there for hemophilia, she has the hemophilia mutation. She's just going to be a carrier. Her phenotype right here, her phenotype is going to be no hemophilia. No hemophilia. She'll have no problem clotting her blood. The only way that a woman could be a hemophiliac is if she gets two versions of these, because this is a recessive mutation. Two versions. Now this individual will have hemophilia. Now men, they only have one X chromosome. They only have one X chromosome. So for a man to exhibit hemophilia, to have this phenotype, he just needs it only on the one X chromosome he has. So, and then the other one's a Y chromosome. So this man will have hemophilia. So a natural question should be arising is, hey, this guy, let's just say that this is a relatively infrequent mutation that arises on X chromosome. The question is, who's more likely to have hemophilia, a male or a female? All else equal, who's more likely to have it? Well, if this is a relatively infrequent allele, a female, in order to display it, has to get two versions of it. So if the frequency of it, let's say that the frequency of it, and I looked it up before this video, roughly they say between 1 in 5 to 10,000 men exhibit hemophilia. So let's say that the allele frequency of this is 1 in 7,000 is the frequency of XH, right? The hemophilia version of the X chromosome. And that's why 1 in 7,000 men display it, because it's completely determined whether, there's a 1 in 7,000 chance that this X chromosome they get is the hemophilia version. Who cares what the Y chromosome they get is, because that essentially doesn't code at all for the blood clotting factors and all of the things that drive hemophilia. Now, for a woman to get hemophilia, what has to happen? She has to have two X chromosomes with the mutation. Well, the probability of each of them having the mutation is 1 in 7,000. So the probability of her having hemophilia is 1 in 7,000 times 1 in 7,000, or that's 1 in, 49 million. So as you can imagine, the incidence of hemophilia in women is much lower than the incidence of hemophilia in men. And in general, for any sex-linked trait, if it's recessive, if it's a recessive sex-linked trait, which means men will, if they have it, they're going to show it because they don't have another X chromosome to dominate it, or for women to show it, she's have to have both versions of it. The incidence in men is going to be I guess we could say it's going. So let's say that P is, or let me write, M is the incidence in men. Incidence, spelling badly. Incidence in men. Then the incidence in women will be what? You could view this as the allele frequency of that mutation on the X chromosome. So women have to get two versions of it, so the woman's frequency is M squared. And you might say, hey, that looks like a bigger number, I'm squaring it, but you have to remember that these numbers, the frequency is less than 1. So in the case of hemophilia, that was 1 in 7,000. So if you square 1 in 7,000, you get 1 in 49 million. Anyway.
Alright, I hope you found that one interesting. As a little note, towards the end of that video where he squares 1 in 7,000, he writes up on the screen 1 in 49 million, although the last 3 zeros do get chopped off the screen there. Now, this PowerPoint is available on our class wiki. I've put everything for this lesson on the front page, so you'll see it up there, labeled as Inheritance 3 Sex-Linked Genes. Just a couple of things to go through quickly, and then I'll give you an example of how to do a Punnett square for sex-linked genes. So, firstly, sex-linked genes are genes located on either the X or Y chromosome, but realistically, what we're going to do in Year 10 is just look at ones that are located on the X chromosome, because, as you heard in the video last lesson, the Y chromosome doesn't do a lot. There's about 70-80 genes on there, but not a huge amount. So most of them are on the X, and that's what we'll focus on today. Remember, obviously, XX female, XY male. So, annotation-wise, you'll remember for autosomal chromosomes, so that's genes that are on autosomal chromosomes, that's chromosomes number 1 through 22, we just use the letter. So, for example, a capital R and a lowercase r to show the dominant and recessive. For X-linked conditions, we do something very similar, except we also have to indicate whether or not the allele is linked to the X chromosome or the Y chromosome, etc. So what we do is we show the sex chromosomes as X and Y, logically enough, and the specific alleles are shown as superscripts, these little numbers just at the top, next to the X. Okay. Now, yes, theoretically you can have one like a Y little n up there or Y big N up there, but we're not going to look at that. We're just going to look at X-linked ones here. Okay, so what basically the individual alleles that you'll see will be either X capital N, X little n, or Y. Okay, so with this example here, if we're talking about hemophilia, which is an X-linked recessive disorder, the normal allele will have the capital N, the lowercase will be the hemophilia allele because it's a recessive condition, and the poor old Y chromosome here has absolutely no allele, so it's kind of useless at this point. There are, of course, both recessive and dominant conditions that are X-linked, so hemophilia is a good example of a recessive condition that's linked to the X chromosome. Okay, so the normal allele is dominant and the abnormal allele is recessive here. So, because it's X-linked recessive, and males only have one X chromosome, if a male inherits the recessive hemophilia-linked allele from, realistically, his mother, then he'll definitely have the disorder. But for females, if they inherit one copy of the recessive allele, either from mum or from dad, and from their other parent they receive the normal allele, they'll be X capital N, X little n, they'll be carriers of the disease, they can pass it on to their children, but they won't show the disease. In contrast, forgive me, in contrast, with an X-linked dominant condition, again, the gene's located on the X chromosome, but the disorder allele is dominant. So if we were going to do vitamin D-resistant rickets, for example, we might use R for rickets as the letter. So X capital R would be the affected rickets-producing allele, and X little r would be the normal but recessive allele. Okay, so with a dominant allele, as you'd expect, if a male or female offspring inherits that allele, they'll have the disorder, end of story. Remember, it doesn't matter whether they're heterozygous, so they've got one copy of the normal and one copy of the abnormal, or if they're homozygous, they've got two copies of the dominant, they'll still show the condition. So just as a quick summary, here of what you might see, okay? So in this table, this is how I've coded it. So for X-linked recessive conditions, look at this as being X capital N for the normal allele, X little n for the affected, Y, no allele. For if the X-linked dominant column, which is down here, X capital N will be the affected allele, X little n will be the normal allele, and Y will again mean no allele. So for X-linked conditions, there's overall 5 possible genotypes, okay, that you'll see written down. Okay, there'll be X capital N, X capital N, X capital N, X little n, X little n, X little n, X big N, Y, and X little n, Y. I've just made it a little bit bigger there to make it easier to see. So if we're talking about a recessive condition like haemophilia, for a starter, if you see someone who's X capital N, X capital N, they're obviously going to be a healthy female because they've got 2 copies of the normal healthy allele. If someone is X capital N, X little n, obviously they're XX, so they're going to be female again. Okay. In terms of their phenotype, though, whilst they'll still be healthy, okay, so they won't show the disorder, but we call them a carrier female because they do have 1 copy of that affected allele, so they can pass it on to the children. Third possible genotype is X little n, X little n, and this is an affected female. So this is a female who's received 1 copy of the abnormal allele from her mother and 1 copy of the abnormal allele from her father, and ergo, unfortunately, she's one of those 1 in 49 million, in the case of the haemophilia allele that was being talked about before, who would unfortunately be affected. Unfortunately, in reality, with that particular haemophilia allele that the gentleman from Khan Academy was talking about before, very, very few, if any, who have this particular genotype actually survive to birth. Now, we talked about the numbers just very, very briefly at the end of last lesson. 1 in 7,000 chance for a male means 1 in 49 million chance for a female, so that realistically that's about 70 females out of the entire population of the planet. Okay, so it's very infrequent to have this sort of situation for an affected female. Very, very infrequent indeed, if it's an infrequent allele. Other option here, X capital NY, which is a healthy male, because here X capital N is our normal allele, so he's got just the 1 copy, and luckily enough he's got the normal one. Whereas this male here, unfortunately, has obviously received the Y gene from his father, that's why he's a male, but has received the X little n from his mother, and unfortunately is therefore affected and will carry the disorder. If we're talking about an X-linked dominant condition here, and please note I've put dominant in all caps just to simulate like we do with the alleles and underline, so please note this is the dominant column here, okay, this is the recessive column here. So for dominant it's a little bit different. So because X capital N is now the dominant affected allele, if you have X capital N, affected female. Equally, if you have X capital N, X little n, again an affected female, because you only need 1 copy of that dominant allele to show the condition, in this particular case, when the condition is dominant. So just to go back over some of our terminology from before, this is obviously a homozygous female, because 2 copies of the same allele. This is a heterozygous female, 1 affected, 1 normal. This individual here will have 2 copies of the recessive normal allele, and therefore they'll be a healthy female. Moving on to the males, who unfortunately again are gene poor in this respect because they have the Y chromosome from dad. X capital N for a dominant condition, they're going to show it. End of story. This individual here has X little n, which in this case is the normal allele for a dominant condition, so therefore they'll be healthy. That's a basic introductory guide to the possible genotypes and possible phenotypes that you see with X-linked conditions. The next video will give you a short little introduction into doing a Punnett square with these particular alleles and genotypes as opposed to the autosomal ones. It's effectively the same but with slightly different notation, so that will be the next video. From here you can also see that this PowerPoint is on the front page of our class wiki. There's also more slides past this slide, so you'll be able to have a look and see a little bit more detail about recessive and dominant X-linked disorders